In this lesson, we'll talk about Wiley Section 10-3, the gas laws. First, we'll review a little bit of kinetic molecular theory. We'll talk about the individual gas laws, Charles' law, Gay-Lussac's law, Avogadro's law, and finish up with the combined gas law. Last lesson, we said that we made some valid assumptions about how gas molecules behave. We said the molecules do not attract or repel each other. The volumes of the individual molecules are small enough to ignore. We say they're negligible. And finally, gas molecules are in constant motion, bouncing off each other and off the walls of their container. The gas laws attach numbers to these assumptions about kinetic molecular theory. We'll start with Charles' law. Named after the French scientist Jacques Charles, asserts that as the temperature of a gas increases, the volume increases, assuming that what is held constant? If it's about temperature and volume, we have to assume that pressure and number of gas molecules are held constant. The mathematical expression of Charles' law is that volume over temperature is a constant, or V1 over T1 equals V2 over T2. V is volume, T is temperature. What units do we use? Not Celsius. We use Kelvin. And just as a side note, we don't say degrees Kelvin. Kelvin is an absolute temperature. We just say Kelvin. At 0 Kelvin, the theoretical volume is 0, which is one reason why we've never reached 0 Kelvin. Where Charles' law related volume and temperature, Gay-Lussac's law relates temperature and pressure. Mathematically, we say P over T is a constant, or P1 over T1 equals P2 over T2. If you look at the following video on YouTube, either follow this link or Google spray paint can and a fire, you will see Gay-Lussac's law in action. These guys put a spray paint can onto a bonfire, the temperature increases, the pressure increases, and eventually the can fails. Spectacularly, I might add. So remember, these guys are the idiots, so you don't have to be. Boyle's law, you will probably teach this in your science classrooms. It's not in the Wiley text, so I wanted to quickly mention it here. Boyle's law is named after the English scientist Robert Boyle. It says that as gas volume increases decreases, the pressure increases. If the volume gets smaller, the molecules strike the wall more often, assuming what is held constant? Temperature and the number of gas molecules. Once again, this isn't specifically mentioned in this section in the text, but you will probably see it and teach it in your science classes. It says pressure times volume is a constant, or P1V1 equals P2V2. Finally, we'll talk about Avogadro's law, and this is a common sense relationship that we see all the time. It says that as the number of gas molecules increase, the volume increases. It's just like filling up a balloon. Assuming what is held constant? Temperature and pressure. Mathematically, volume over N, which is the number of gas molecules or number of moles, is a constant, or V1 over N1 equals V2 over N2. Now we'll combine the gas laws. If we combine Charles, Gay-Lussac, and Avogadro's law, we get the ideal gas law. Let's look at that now. Charles' law, volume over temperature a constant. Gay-Lussac, pressure over temperature a constant. Avogadro's, volume over number of gas molecules, is a constant. Those all come together to give us pressure times volume over number of molecules times temperature equals a constant. What is that constant? It's symbolized by R, and it's called the universal gas constant. Anybody know its value? It has different values depending on what units you use. Let's calculate that now. Experiments have determined that 1 mole of an ideal gas at 273 Kelvin, which is 0 degrees Celsius, under 1 atmosphere pressure occupies 22.4 liters. We're going to use this information to calculate R. If you've got your calculators handy, go ahead and run these numbers. I'll pause for just a minute. I get 0.0821 liter atmospheres over mole Kelvin. You won't have to memorize this value when you are working ideal gas problems. You will be given this value for R. So in this lesson we discussed the mathematical relationships that cover how ideal gases behave. The next step is to solve problems using the individual and combined gas laws. The main job of your course mentors is to enable your success in these courses. You can email us at the group inbox at chemistry@wgu.edu, or you will find contact information for your individual course mentor in your course of study.